Hello and welcome to this lecture. We are going to talk about change of basis. Now we'll look at two things and what happens to them under change of basis. One is the coordinates of a vector. So you remember when you think of an abstract vector and you fix a basis for the vector space, you can get a list of coordinates. I mean, we are thinking of finite dimensional vector spaces, so a list of finite coordinates that will come once you fix a basis, right? Now when I change the basis, we are always keeping the abstract vector as some fixed quantity, right? So the vector itself remains the same. The coordinates will change as you change the basis. So the same vector has different lists of coordinates depending on the basis that you pick. Okay. So how does that happen? Given one coordinates with respect to one basis and given another basis, how do you go from this coordinates to the next coordinates? Is there like a very systematic, easy process? That we'll describe. The same thing with linear maps also, right? So you have an abstract linear map once again that I've defined from V to W, which works on a vector V, it takes you to TV. Now, once I specify a basis for V and a basis for W, you know how to write down a matrix for this linear map. And what does that matrix do? You take coordinates for a vector V in that basis, multiply on the right, multiply this matrix on the right, you will get the coordinates for the vector TV in W. Okay, so that's what happens with this matrix convention. So now what I can do is, the linear map remains the same, but the basis in V and the basis in W are going to be changed. Then what's going to happen? What's going to happen to the matrix? What's going to happen to the operation? Because it's the same linear map, but it's being thought about in another set of bases. Okay, so these are the two things that we'll look at in this lecture. So let's get started. A quick recap as usual before we start. We've been looking at a whole bunch of ideas, and the last couple of lectures we saw this notion of different subspaces associated with the matrix, the four fundamental subspaces: column space, row space, null space, left null space, and all of these things are very important. So when you see a matrix, you should think of all these guys, and they tell you a lot about the linear map that it represents. And the determinant of a square matrix, we saw that function in the previous lecture. We saw that this function has many interesting properties. It tells you so many nice things about the linear map once again, particularly invertibility and nice things. And it's preserved under the matrix algebra in a very nice way. Transpose doesn't change it. Multiplication has a simple relationship and determinant. So it's a nice function to know and be familiar with. Okay, so that's a recap. So let's get into this coordinates and change of basis. Okay, so we know this already. You have a basis for a vector space V, and any vector V can be written as a linear combination of the basis vectors, and those coefficients you collect them together and you call them as coordinates with respect to a basis. So whenever you write a vector V, usually people even write V equals the list of coordinates. I'm writing this arrow notation here. That's because in this particular lecture I'm talking about change of basis and all that. So let's not say V equal to one thing here and the same way equal to something else there. It just looks a bit bad. So I'm putting this arrow. But usually, you can write V equals if the basis and all is clear in the context. Okay, so this is something we know. We've seen this quite often. Now, what am I doing? I'm going to change the basis. Okay, so when I change the basis, what will happen? I have to list out the next basis, which is V1 prime, V2 prime. Let's say till Vn prime. I'm calling that basis as B prime. Now, the starting point is the original basis vectors V1 to Vn. Each of them can definitely be written as a linear combination of the new basis vectors, right? So that we know for sure. So let's do that. Okay, so you write Vi is Bi1, V1 prime, so on till Bin, Vn prime. So I do that. So I have these coordinates for Vi in terms of the V primes. Okay, V1 prime, V prime, etc. Okay, so once you have that and you have V written as a linear combination of the V1, V2 to Vn, you can plug it in and infer the coordinates of V in the new basis. Okay, so that's what we'll do. We'll take these Vi's and then plug them into the formula here. Okay, so you do that, then you will get this nice looking equation. So this V is represented by B11 to B1n multiplied by A1 plus so on till Bn1 to Bnn multiplied by An. So if you want me to write a little bit more detail, this guy is V1, okay, and this guy is Vn in what coordinates? V1 with respect to B prime. Okay, so likewise here Vn with respect to B prime. Okay, so those are these vectors here, and once you write that, this equation is sort of true. So you put A1 here and then write the V1 coordinates here, so on. Now this product of vector, column vector multiplied by a scalar on the right and added up can be conveniently represented as a matrix product. So you get this matrix times the coordinate system, okay, the original coordinates. Okay, so once again notice this. This is coordinates of V with respect to B. Okay, so this is sort of like the matrix representing change of basis. Right. So you get a matrix representing change of basis. How do you find this matrix? Every column, the ith column is Vi, the ith basis vector of the original basis represented in the new basis. Okay, how do you express that? So that's what each column is. Once you write that down, you get a matrix, and that matrix sort of gives you a method to transform the original coordinates to the new coordinates. After you do the multiplication, you get the new coordinates. This whole thing is coordinates of V with respect to B prime. Okay, hopefully that's clear to you. So that's what happens when you do coordinate transformation. So coordinate transformation under change of basis seems quite simple, right? So you have an original list of coordinates. When somebody says change of basis, you go find this matrix. You go find this matrix and you multiply the original coordinates on the right, you get the new coordinates. Okay, so it seems like a simple enough thing that you can do. Okay, so remember this matrix here that you have, it will be an invertible matrix, right? So you can see that this V1 prime to Vn prime are linearly independent. You take the coordinate systems, coordinates corresponding to each of those guys, they will also be linearly independent. So the columns are linearly independent. So this becomes an invertible matrix, and the opposite is also true. Suppose somebody gives you an invertible matrix, you can think of that as a matrix representing basis transformation, right? So why? Because you can imagine a basis with the columns of that matrix being the new basis. Okay, so you take any invertible matrix, the columns are linearly independent, and together they span the space. So you can imagine a new basis being just defined by this matrix, right? So this matrix not only represents the change of coordinates, it also represents the new basis itself. Okay, so that's a nice thing to remember. So this thing, so you should keep in mind. So when somebody gives you a matrix corresponding to a coordinate transformation, the basis itself is hidden there. The new basis itself is basically the columns of that matrix. Okay, so these are all nice things to remember. Okay, so how do you go back? Okay, so you changed from B to B prime. How do you go back from B prime to B? Is it related in any way in going from B to B prime? It turns out there is a very clear and simple relationship. So we know that going from B to B prime is multiplication by this matrix. Now suppose somebody gives you a V prime, which is in the basis B prime. You know that there will be a matrix corresponding to B prime to B. What will that be? That will be the first column of this will be V1 written in terms of the V primes, right? So be careful again. So this matrix here, the original matrix is going from V1 written in terms of V1 prime. So this will be V1 prime written in terms of V. Okay, so should be a little bit careful here. This one is V1 prime with respect to B. Okay, so like that. So each column, the ith column will be the Vi prime written in terms of the basis B. Okay, so you write that. Okay, so now what's interesting about this these two matrices, you can see that these two matrices have to be connected. One is going from B to B prime, the other is going from B prime back to B. Okay, so what will happen is that this matrix will be the inverse of that other matrix. Why? Because you take any vector V, any coordinate V, you apply this first matrix to go from B to B prime, and then apply this second matrix to go from B prime to B, you better get back the same original list of coordinates, right? You can't get some other coordinates. So these two matrices better be inverses of each other. You should get the identity when you multiply them together. Okay. So if you want, you can write down a clear proof for this. It's not very difficult to imagine how you will write a proof. So these two matrices have to be inverses of each other. Okay. So so when you multiply them, you should get identity, right? So that's how we define the inverse of a linear map. So these two have to be inverses. Okay. So good thing to remember this. When you use a matrix to go from one basis to another, the inverse of the matrix will take you back. Okay. So that's something to remember. Okay. That's good. Okay. So now we're ready. Hopefully we've seen how to change coordinates. All that is clear to you. I'm not giving examples for coordinates. I think it's easy enough. Maybe I've given that example before, but hopefully you have enough practice to write down examples of your own if you want, for examples for coordinate transformation and how going from one to the other will be based on very simple inverses and matrix multiplication. So I'm skipping examples for that. I'll give you examples for linear maps though. Okay. So let's talk about linear maps. You have a linear map T that goes from V to W. Once you fix a basis for V, like I fixed here, some basis for V, and a basis for W. See, I'm going to pick the dimension of V to be N and dimension of W to be M, like before. Okay. So I'm using this notation BV and BW for a basis for V and a basis for W. Once I fix that, I can make a matrix for my linear map with respect to BV and BW. Okay. So you know how this is done, right? So you take each of the basis vectors from V, do a transform with the linear transformation T of V1 to T of Vn, and then you go take T of V1, which actually belongs to W, write it as a linear combination of BW, of vectors in BW. Okay. What coordinates you get, you put in the first column. Okay. So that is T of V1. That's the first column of this matrix. Okay. So likewise, you do the second column, third column, last column will be for T of Vn. Okay. So you get a M cross N matrix, which looks like that. Okay, so that's the matrix. Okay, so that's what I've written down here. The ith column is coordinates of T of Vi, and that would be Aij. Okay, so that's how we write. So how do you compute coordinates for T of V, right? So given a vector V, you first express it in the original basis BV. Okay, so as a linear combination of V1, and then you apply T to it. You know that this T is a linear map, so it preserves linear combinations. So you get B1 T of V1 plus so on till Bn T of Vn. Okay, so that's your T of V here. Okay, so V to T of V. How do you write it in terms of coordinates? You take the matrix that you got representing this linear map, multiply on the right with the coordinates of V. Okay, the coordinates, whatever coordinates of V you got. Overall, finally, you will get the coordinates of T of V in the basis BW. Okay, so this is the product. All right, so I'm not, maybe I should write this in some detail. This is coordinates of V with respect to BV. This is the matrix, right? So this Aij is the matrix with respect to BV, BW. This whole thing is coordinates of T of V with respect to BW. Okay, so this is the simple little result that you get. So this we've seen before, how to represent, how to find the matrix corresponding to a linear map, and how do you use the coordinates to compute input and output. Given input coordinates, what will be the output coordinates, and so on. Okay. So let's take a few examples. The first example I always like to take is the simplest possible linear map, which is the identity map, right? So identity map, simply given a vector, outputs that same vector. Okay. So now notice I can do some interesting things here. The first thing is I need a basis for the input and basis for the output. Okay, but remember this is V to V. Okay, so identity map means V and W are the same, right? So maybe I can pick the same basis for the input and the output, okay, which is a good thing to do. We'll see later on that it's crucial sometimes. Okay, so you pick the same basis. If you pick the same basis, then it's very easy to write down the matrix corresponding to the identity map. You will get the identity matrix. It's easy to see, right? So because I of Vi is simply Vi with respect to BV, So you write that, you will get 1 0 0 0 0 1 0 0 0 0. Okay, so it's very easy to see how you get the identity matrix, right, under this map. Now what I can do, which you probably don't want to do for the identity map, but let's try it, see what happens. For the output, instead of using the same basis BV, maybe I want to use another basis, B prime V. I can do this, right? So nothing stops me from doing that. Okay. So now what will happen is, what will happen to the ith column of the matrix now? I will have I of Vi being Vi, because that's the identity map. But I have to write Vi with respect to B prime, right? The output I don't write with respect to BV, I write it with respect to B prime V. Okay, so that's what I do. I get a new matrix for I, okay, where I of Vi, which is Vi, I write with respect to B prime V. Okay, so once again, to remind you, this is V1 with respect to B prime V. Okay. If it were V1 with respect to BV, I will get 1 0 0 0 again. But if it's with respect to another matrix, another basis, I'm going to get some other coordinate, right? So that's what I'll get here. Okay, so remember that. But likewise, I find column after column. So now to notice what has happened here. It's interesting what has happened here. What will you get here? The matrix you get here is exactly the same matrix you got when you looked at change of coordinates with respect to change of basis, right? If you take coordinates for V and you want to change the coordinates to B prime, right? Coordinates for V with respect to BV, you want to change it to B prime V, then you got the same matrix. You had to write the exact same thing again. So what you were doing for this coordinate change with respect to change of basis is nothing but changing the basis, input and output basis in the identity map. Instead of keeping output basis equal to input basis, you changed it to some other basis and then you saw what happened. Okay, so that's the idea behind what's going on. So this is a nice way to think about change of coordinates. So change of coordinates is actually a linear operation. It's the identity map when you change the output basis to something else. Okay. You can also do the change of basis and back. Okay. So you see that you can keep the input basis as B prime and the output basis as BV, right? So now if you do that, you will get the inverse, right? So you got, if S was the first matrix, you will get S inverse here. So this is the same as what we saw before. Okay, that's good. So now let's look at an arbitrary linear map. Okay, T from V to W. I have a basis for V, basis for W. I found a matrix. Okay, what happens when you change basis? Notice what's going to happen. Let's say instead of BV, I'm going to pick another basis, B prime V here. Instead of BW, I'm going to pick another basis, B prime W. Okay, so that's what I'm going to do. And now I ask the question, what's going to be the matrix of the linear map T with respect to this new basis? Okay. This is a simple view. You can view this as some sort of a composition. Okay, so this view is very interesting. It's very simple and at the same time immediately tells you how to go from one matrix to another with respect to one basis to another matrix with respect to another basis. So notice what I'm doing here. This change of basis operation, I'm going to view it as some sort of a composition for the overall transformation. Okay, I know the transformation from BV to BW, but my vector input is being given in B prime V, right? So that's what this means, right? When I want a change of basis, I want to specify my input as a linear combination of B prime V, and I want you to give me the output as a linear combination of B prime W. That's what I want when I say change of basis from B prime V to B prime W. So my input coming into my T is not from the basis BV, but from the basis B prime V. So what do? I first hit it with the identity map with input basis BV prime and output basis BV. I know how to do this. Basically, I do a change of coordinates from B prime V to B and then use the same T and the same matrix for T which I know from BV to BW. Okay, I use that matrix, I go from BV to BW. But I don't want the output in BW, I want it in BW prime. What do? I hit the identity map again, which goes from BW to BW prime. I change basis in W from BW to BW prime. So this is what I need to do a change of basis for a linear map. Linear map T is specified as a matrix given a particular basis BV, BW, PV and BW. I want to now change basis to B prime V, B prime W because my inputs maybe are coming from another basis, right? So how do I do that? I first do this identity map which takes me from B prime to B and then hit it with the same matrix as before, takes me from B in the representation BV to the representation BW, and then you once again do this identity map with basis being different. So when I say identity map, it refers to change of coordinates, right? So that's what happens. So you do that, you get this. So in terms of matrices, I have the matrix for T sitting in the middle. To its right, I'll have the matrix for the identity map in V, okay, basis B prime V to BV. And then on the left, I will again have a matrix for the identity map in W, which will be from BW to B prime W. Remember, both of these will be invertible. This will be an invertible map. This will be an invertible map because it represents the identity map, right? Just that the bases are different, but it's going to be an invertible map. Okay, so that's it. That's all is there into change of basis for a linear map, right? So instead of just thinking with that matrix, I know the basis has changed, so I put in my identity maps in front and right and left to convert to the basis I have, and then go back to the basis that I want. Okay, very simple idea. Okay, so now what happens for operators? Okay, it's not really too special or terribly different, but notice for operators quite often you may want to keep the input and output basis as the same. You don't have BV and BW, you maybe have the same basis, okay, and then you can compute the matrix for T, and maybe I want to go to a change of basis, but again input and output are the same. I may keep the input and output as the same, right? Maybe it can be different also, we will look at that case later on, but you may want to keep the input and output basis as the same for linear operators, and this is a very popular choice. There are good reasons for why you want to do this, but let's say I want to do this, then what will happen? Notice you know what happens when you do this, right? You will have the matrix for T, which will be SA S inverse. S is what? And S inverse is what? S will take you from BV to BV prime, okay, and S inverse will take you from BV prime to BV, okay. So that's the map you will get, because notice what you have to do at the output, you have to go from BV prime to BV, okay, so you will get a S inverse map there, and then you hit it with the same matrix A, which is from BV to BV, and then on the left hand side you will have the identity map from BV to BV prime, okay. So that is what we have as S, and so here you will have the S inverse. So you have this nice looking transformation of matrices when you do a change of basis from BV to B prime V in an operator with an operator, the same V to V, then the original matrix gets transformed as SA S inverse, okay. S represents the transformation from BV to BV prime, the coordinate change from BV to BV prime, which is an identity map with input and output basis different. Same thing with S inverse, which is in the other direction, okay. So this is a nice looking transformation. In fact, it has a name. It's called a similarity transform. You can pick S as any invertible matrix. We know that also. SAS inverse represents change of basis to columns of S. Okay, so remember this is the columns of S, and S should come on the left. That's the new basis that you're going to from the original basis. Okay, so that's important to understand. Okay, okay. So I'll stop with this. Hopefully you can see how this works. Okay, so maybe we should do a example or two. Maybe we should do an example here to see what I mean. I'll do R2 examples, which is easy enough. Okay, so let's look at a matrix A, which represents some linear transform. We'll take a familiar matrix or famous matrix that I always write down. So this, say it represents some linear map with respect to the standard basis. Okay, so we'll say standard basis for input, standard basis for output. Okay, so let's say BV. So let me write it down. BV is 1 0 0 1. Okay, that's good. So now I might want to go to another basis, which is say B prime V. Maybe that is 1 2 and 3 4. Okay, is this a basis? Yeah, it's a basis. You can check that it's a basis. What do I have to do? I have to find this S, which is going to do the coordinate transform from BV to BV prime. Okay, BV prime. So a lot of people have a lot of confusion about change of basis, because I mean they say, okay, B prime, I have written coordinates here. What do these coordinates represent? Okay, these coordinates also need a basis, right? So usually the hidden assumption is when nothing is given, it's always standard basis. So this B prime V has to be represented in BV only. Only then you can do the transformation properly. Okay, remember this is all with respect to BV. Okay, so these coordinates are in the original basis that you specified. If this itself is different, you have to change this also. You have to assume that these coordinates are with respect to BV. Okay, so that's sort of a tacit assumption. It's not explicitly mentioned usually, but that's what it is. Okay, so my S is what? S is going to be what happens. So I have to write 1 0 in terms of 1 2 and 3 4. So what is the first column? Remember, it's 1 0 written in terms of 1 2 and 3 4. So you have to sort of do like an inverse calculation. So let's try and do that. If I want 1 0 in terms of I can do, I think, minus 2 and 1. I think this is true. Minus 2 into 1 comma 2 plus 1 times 3 comma 4 is equal to 1 0, right? So that's good. Okay, so I've already got that. This is my S, minus 2 1. This is 1 2. This is 1 0 in B prime V, right? This is my S. The next is 0 1. I have to get 0 1. So for that I'll have to do I think 3 times 1 2. If I do 3 times, I'm going to get 0 here. That will be, so maybe 3 by 2 times 1 2 minus 3 by 2 times 3 4. Okay. So I think, no, minus maybe 1 by 2. Okay, yeah, I think this works. This would give you 0 1. Okay, so this is how you figure it out. So this would be 3 by 2 and minus 1 by 2. So what did I write here? I wrote 0 1 in B prime V. Okay, so this gave me my S. This is the transformation from standard basis coordinates BV to B prime V. Okay, so you can also do S inverse. Now S inverse you can do in two ways. Okay, you can directly find the inverse of S if you know some standard method, or you can work it out in the way we did it, right? So what will be S inverse? S inverse will be, it's a transformation from BV prime to BV. So I'll have to write 1 2 in terms of this coordinates, and that is very easy to write. So you'll just write 1 2. Okay, I hope I got this right. Okay, and then you'll write 3 4. Okay, so this is very easy to write down, right? So this is basically 1 comma 2 in BV, and this is 3 comma 4 in BV. So it's very easy to write down S inverse. Okay, S inverse is very easy. S is just the inverse. You can check that these two are inverses. If you take this and multiply with this, I think you should get it. Okay, so it should work out quite okay. I think it should be fine. It looks okay to me. So this is the inverse. So it's a S inverse. So what about the matrix? If you go from here to change of basis BV to BV prime, you'll have to do the S inverse. Okay, so S takes you from BV to BV prime, and then from the standard basis to the new basis, and then S inverse takes you from the new basis to the standard basis. You multiply with your A, you get the answer in standard basis, and then you go from standard basis to the new basis. That is SA S inverse. I'm not going to do this product. You can figure it out. Okay, so these are the steps that you use to calculate change of basis for linear maps. Okay, so hopefully this was clear to you. Hopefully this example was also very useful. Okay, so we'll stop with this lecture at this point, and then move on to the next lecture where we will see why change of basis is interesting to do in the context of linear maps. Thank you.